Hello, are you able to view the window? There is written Newton's second law. Okay, so I'm starting my presentation. Before that, some students are waiting. Okay, so in our previous discussion, we had a talk about classical mechanics and Newton's second law. Now, today, our topic is Newton's second law. You have already seen. Now, let us start from measuring forces where we had stopped in our previous discussion. Hope you can remember that we had one spring system on which we calibrated uh, for a particular uh, body, for a particular specified body, we have calibrated for what amount of extensions or delta L, what will be the amount of acceleration, and for particular acceleration such as 1 unit of acceleration, 1 meter per second square, we have called the responsible force as 1 unit force. Similarly, for 2 meter per second square acceleration, we had defined it as 2 unit force, and 3 meter per second square 3 unit force, and so on. Now, another way to measure force we can find, that is electronic force probe. Here in the figure you can view one electronic force probe, okay, which can be interfaced to a computer. Okay, so in computer, when it is interfaced to a computer, we can directly read the reading of the force, the measure of the force in the computer screen. Probably we can record it to any Excel sheet or any other sheet if you prefer, and we can find the nature of force, we can find the variation of force continuously, we can get the graphs and so on. So it will be a better system. Now, how this machine has been built? Basically, in our previous discussion, the extension was converted into force. Okay, that's why the calibration was needed. So we were converting extension into force, but this time here is an electromagnetic device, typically called sensors, sometime maybe a load cell. When force is applied to that, that is an electronic device. What happens if force is applied to that? It generates some potential, electric potential or voltage, which can be measured. Now, for a particular amount of force, some particular amount of potential is generated. Now, if we have already calibrated that for how much force, how much voltage is generated, then next time only reading the voltage, we can say that this is the amount of force this time. Okay, if already known to us that this much potential is for that much of force, so only reading the potential, only reading the voltage difference, we can get idea that this much force has been applied. By following this principle, we can measure forces. Now, right now, let us discuss about what is mass. I know all of you know what is mass, but for the sake of understanding it from the concept of Newtonian law, let us all forget about the basic theory. Just remember what we have discussed in my earlier class. We don't know what is mass, or mass is a quantity or anything. Now let us start from the zero. Now, in our previous section of discussion, we had a series of experiments. Hope you remember. We had a series of experiments of spring and the specified bodies, where we had given some extension in order to get some acceleration, and we had measured forces. Now, this is the time where we can find that what is the effect of same force if the if the quantity of the object is multiplied. Okay, how we can find out that? Now, before that, we already know, we have some experience that uh, when we try to push a bicycle, it is much easier than pushing a car, and pushing a car, it is much easier than pushing a truck. So the question arises that what makes these bodies differ in our ability to accelerate them by pushing them. Okay, so when we are trying to accelerate them, you know that when a body is at rest, if you try to move it, if you want to give some motion to it, that means it is accelerating. And otherwise, when a body is at constant velocity, moving in a straight line, then also if you want to increase its velocity, then it is called positive acceleration, or even if you want to change its direction, then also it is called an acceleration. So the question is, when we are trying to accelerate, the bodies are resisting the acceleration. Now this resistance power is different for different bodies. This resistance power is very less for bicycle, but it is higher than the bicycle for a car. Now we will do an experiment right now. What will be the experiment? Now, initially we have taken one standard body that we had already defined, that what is a standard body, which is identifiable, easily identifiable and reproducible. So that type of standard body, probably maybe you can assume that block made of steel. So that block we have taken, and what we are doing, initially we have already a calibrated spring. So in that calibrated spring we had taken 1 unit of force, and for one standard body we have checked that what is, after applying 1 unit of force, what is the acceleration. So it would be 1 meter per second square, as we know. It is exactly doing what we are expecting. Next time, let us increase the force to 2 units, and it will be showing 2 meter per second square of acceleration as expected. Then if we apply 3 units of force, then it will be 3 meter per second square as expected. And if we apply 4 units of force, it will be 4 meter per second square. You know this very well. Now next time what we will do, we will add another standard body which is identical to the primary one. It looks like same, and you can guess that the quantity, okay, within the body, the quantity is also almost same. So if you add another body and connect them, then we can call it two standard bodies, basically two units. Initially it was one unit, and this is two units. And if you apply force of one unit to it, you will see that the acceleration is half half of the previous one. If you apply 2 unit, then also it will become half. That means initially it was 2, it will become now 1 meter per second square. For 3 and 4 also, these are showing that half. So when we are making the standard body, number of standard body double, the acceleration are becoming half of the previous one. This is a stage 2 experiment. Now we are moving to stage 3. So in stage 3, we have connected 3 standard bodies together. So the standard body is multiplied into 3 times. 3 units of bodies are there. Then if you apply 1 unit of force, you will observe that 1/3 of the acceleration as the previous one is obtained. Again, for 2 units of force, this is 1/3 of the first one. For 3 also, for 4 also, each time this is 1/3. So what is our conclusion? That when we are applying 2 unit of bodies, then for same applied force, the accelerations are becoming half. Each horizontal row, you see that this is the half as the half of the first horizontal row. And in case of third row, when it is the quantity of the body is 3 times, then it is becoming 1/3 in case of acceleration. So the force are not changed. If you only change the quantity of the body, then there is a change of acceleration. So a same force cannot create same amount of acceleration. Something which is within the body which differentiate them in terms of acceleration. Now let us see the experiment once again in picture, so you can get the idea better. So this was the 1 unit of body, the block on which 1 unit of force we have applied. Okay, and acceleration is this much. It is shown by one vector. Now this is when the force we have increased into 2 units, obviously the acceleration will be increased. So this arrow is of larger length, and when it is third unit of force, then the arrow is more larger. So in a row, what is our observation? In a row, if you move rightward, the force increases, and as well as the acceleration also increases. So with the increase of force, the acceleration increases. But what happens if you come downward? So first thing you observe that the amount of the body, number of the bodies, they are from 1 to 2 in count, from 2 to 3 in count, and they are, as they are increasing in count, the acceleration is becoming smaller and smaller. But for a particular amount of body, if you increase further the force, then acceleration will increase. But in any column you can compare that always the acceleration in the first item is larger, then it is smaller, then it is further the smallest. So it is decreasing downward. It is decreasing downward. Okay, so this is the tendency. So what we can conclude that for each connected bodies, the acceleration is directly proportional to the force. Okay, do you agree that the acceleration is directly proportional to the force? Because when we are increasing the force, the acceleration also increases. So acceleration is directly proportional to the force for all the rows. If we increase the force, the acceleration also increases. the proportionality constant between the force and acceleration. Now, if acceleration is proportional to the force, if F is proportional to the A, where F is the force, A is the acceleration, then there must be existing some constant of proportionality so that we can convert the proportional relation into an equation. So, if the constant of proportionality is K, then we can say that K, then we can say like this, that F is equal to K, constant of proportionality, into A. F is equal to K into A. We can say, okay, so where F is the force and A is the acceleration, and what is K we don't know. Okay, so what is the constant of proportionality we don't know. Now the property of the object, let us call it mass, which gives the proportionality constant between the force and the acceleration. Okay, so K mass is nothing but the F by A. Okay. Now, if you look at this chart, you will find the downward direction. What is changing? That constant of proportionality is changing, and that is nothing but mass is changing. Okay, so constant of proportionality changes. That is why this relation is also changed. This relation here, it is 1 into 1, 2 into 1, 3 into 1. So 1 is the constant of proportionality here. Okay, but here it is half. It is 1/3. So only the constant of proportionality is changed. Acceleration is basically force divided by K, force divided by mass. So we are dividing it. If we to get the acceleration, we are dividing force by constant of proportionality mass. Here mass is 1, so 1 divided by 1, 2 divided by 1. Now in the second row, what is the value of mass? 2. So 1 divided by 2, 2 divided by 2. Here what is the what is the value of mass? 3. So 1 divided by 3, 2 divided by 3. In this way, so this is our conclusion. So now we can get the idea of mass. Now till this point, if anybody have any confusion, you can ask me. You can unmute yourself and you can ask me if anybody have any confusion. Okay, I guess you don't have any confusion. Now, from the above discussion, what we can get, we can write an equation. So we can, before doing that, we can repeat the experiments, okay, which are similar to this, and we can conclude that if the mass increases further, suppose we have taken up to 3 units of mass. If we take 4, 5 or larger mass, the acceleration will become smaller and smaller for a constant force. That is, the acceleration produced by a given force is inversely proportional to the mass. Okay, so acceleration is inversely proportional to the mass being accelerated. The mass of a body can thus be regarded as a quantitative measure of the resistance of a body to acceleration. So initially we were finding that what is the property of the body which is offering resistance to the acceleration, and that is nothing but the mass. So we can conclude this here. Now we can write for a fixed force. For same force we can write that suppose initially your standard mass is taken. For standard mass for a particular force, the expression was a standard. For m standard mass, expression was a standard. And now we have changed the mass, either increased or decreased. uh, it is changed to m suffix x. So the expression will also be changed. It will be a suffix x. So we will observe this relation. Okay, mx by mstd is equal to a std by ax. So it is showing that the relation are inversely proportional to a constant f. Now we can further add to this extension, extend this relation. If you apply a different force, you can apply a different force uh, to this. So suppose in place of f, we apply right now f prime. So what will happen? The expression will be changed. A standard dash prime, ax prime. But this will also show a same ratio as the earlier one. So the ratio is not changing. If the mass ratio is fixed, the ratio of the expression will also not be changed if the force also changes. Okay, when the force is also changing, but the mass ratio is same, then acceleration ratio will be constant. So from the above discussions, we can summarize now to an equation that sigma f summation of all the forces in vector form. Why in vector form? Because the force may not only be in one direction x, but it can also be in y and z, all the directions. And as acceleration is also a vector, so we are representing acceleration in vector form also. So sigma f is equal to m into a in vector form. So this is the vector equation of the summary, which is the summary of the discussion. And this is nothing but Newton's second law. Now in this equation, what does f represent? F represent basically fx, fy and fz. It has three components, and if you add these three components, I think you should remember a little bit of your vector mathematics in your school from your school days. That if you add all the components of vector by vector addition, then you can get the resultant vector. So f is the resultant vector which have component as fx, fy and fz. Similarly, a have component as ax, xy and az, and mass is the constant. It's obviously a scalar, not a vector. So this is the elaborated form, you can say. Now let us compare first law with second law. Now in the second law, if you put a is equal to 0, or if you put f is equal to 0, then what will happen? M is not 0, because always we have some quantity of specified bodies. So if a is not 0 and f is 0, that means a is 0. What does it mean? For sigma f is 0, then a is 0. What does it mean? That if there is no net force working on the body, then the acceleration is 0. And this is nothing but first law of motion. Newton's first law of motion states that if no net force is working on a body, then the body will be continuing its state of rest or motion in a straight line with constant velocity. So that means a is equal to 0. If delta f equals to 0, then a equals to 0. So there is a question that whether Newton's first law is only an extension of second law, then what was the requirement of statement in the first law? Newton was a big mathematician. He could easily only write one law or single law, Newton's second law. What was the need of Newton's first law? The answer will be Newton's second law does not tell about inertia and inertial frames. Okay, however, the first law has independent and important role in defining inertial frames. Without that definition, we would not be able to choose the frames of reference in which we can apply Newton's second law. Okay. From first law, what we are getting? We are getting Newton's reference frames. Okay, inertial reference frame to which we can apply Newton's second law. That's why both laws are very, very important. Now let us see about the dimensional stability of the equation. Now this is the equation x equals to ma. So the right hand side and left hand side of the equation must be showing the same dimension, otherwise it will not be called as dimensionally consistent. Now what is the dimension for force? We know the dimension for force is ml t to the power minus 2 or ml by t square, and if you see the dimension of m into a, then also you will get m means m and a means acceleration, so l per t square, so ml by t square, the same dimension, so that means the equation is valid. Whenever you in future, whenever in future in physics you want to write some equation, you want to generate some equation, then every time you must check the dimensional validity of that equation, otherwise it would not be valid, or it would not be applicable to any physical thing. Now students, up to this, you tell me whether you have any doubt or not. Nikhil? Okay. Apurvo, Rahul, Pranav? You can unmute yourself and you can reply me if you have any doubt. So can I go forward? Okay. Now we will be trying to solve some problems. Okay. We will see how to solve problems using Newton's second law. We will see some steps. If you follow those steps, you can solve problems. The figure, you can see that this boy is trying to give acceleration to this large stone, and this boy is trying to acceleration to a small stone, and you know that this would be difficult, this will be much easier. Okay, but when you try to solve this type of problems numerically, then you get confused many times. So in order to avoid those confusions and get success in solving those problems, we have to forward stepwise. So first we need to choose a suitable inertial frame. Okay, we already know what is inertial frame. So which frame the law of inertia is applicable, those are called inertial frames. Now we need to first select the frames, okay, to which it is applicable. Just like in this figure, the table, we can consider this table. to be an inertial frame, rear frame. Then we need to see whether this table is inertial frame or not. If the frame is inertial, then the Newton's second law is applicable, otherwise not. Then we have to find out the force components. When the force is applied, suppose this force is applied to the string. So the string is not, if the we need to specify the coordinate system also. So if this coordinate, leftward coordinate is positive x-axis and the upward side is positive y-axis, so opposite sides will be positive x and positive y-axis. So in this coordinate system, we can find that the, okay, let us show by pen, then it will be easier. So this is the y-axis and this is the x-axis, and the rope, it is the direction of the force, and it has some angle with the x-axis. Okay, it has some angle with the x-axis. So we need to decompose the force. Okay, we need to find out the component of the force. One component will be acting this side and another component will be acting this side. We know that this will be F if the force is F, this is F cos theta, and this side F sin theta will be acting. So we need to decompose these forces this way. Okay. So if anybody don't understand or you have forgotten from your school level, discussed from your school level syllabus, with how to decompose the forces, how to get the vector components. So don't worry, it will be just discussed later, because in the prerequisites we will discuss all the primary things which we will require. So this way we need to decompose the forces. So after decomposing the forces, we need to find out whether the directions are positive or negative. These are the positive direction we have specified for this problem. So if you find the component this direction, then that would be negative. So we can then go to the next second step, which is drawing a free body diagram. What is a free body diagram? Free body. Free body means make the body free from all of its contact surfaces. So the body is the, suppose the body is the stone, which is our focus. So the make all the contacts free. So what is the contacts? Rope is there, the table is there. So remove them. So keep only the stone. Then this is the free body diagram, and also show the forces acting over it. So what will be the forces? Maybe one weight will be acting downward, and one reaction force will be acting, and this applied external force is also acting. So this will be the forces acting over it. So the free body diagram will only contain the body and the forces. Then the most important thing, we need to label the forces by subscripts. Okay, why we are doing so? Because when we draw free body diagram, sometimes what happens, if there is a number of forces, okay, if huge number of forces are in the problem, then we often get confused that which forces are required to solve which free body diagram and which forces are not required. So sometimes we include some unnecessary forces, some irrelevant forces, and we do mistake. Our results become having some our results have some error due to that. So in order to avoid that kind of silly mistakes, we give nomenclature to the forces. What is the nomenclature? It's like FAB. F representing force and AB, it has two subscripts A and B. What does A mean? A indicates the force on body A. So on which body is it is acting? A. That's why first subscript is A. Then from which body it is coming to body A. Okay, or the force on body, but due to which body? Force on body A is due to body B. So that's why second subscript is B. Similarly, if it is FBA, that means the force on body B due to body A. Okay, so this way, if we name it nomenclature, we give names to all the forces, then there is no chance to include any unnecessary forces. Suppose when we are drawing the free body diagram of body A, and if some force have subscript as FCB, so there is no need to include that because there is no subscript of A. So this way, the nomenclature step we have to follow. Then after that, we have to find the vector sum of all the forces. Okay, and uh, usually it means separately adding, okay, x y z components of the forces. We need to find out x y z components, and we need to vector addition them, and then we need to solve for the equation that was mentioned here. F is equal to ma. This vector equation we need to solve, then we will get the solution. So one sample problem is for you. In this sample problem, you can see that the one worker is pushing one loaded sled, okay, whose mass is given 240 kilogram. This loaded sled, okay, this is mentioned by S. This mass is given 240 kilogram, and it is pushed for 2.3 meter, for a distance of 2.3 meter over the surface of a frozen lake. Okay, surface of a frozen lake is given. So probably they will also give the it is friction is negligible. How? The straight move with negligible friction on ice. Okay, so you don't need to consider the friction. The worker exerts a constant force FSW, constant horizontal force. That means it does not change. Okay, force does not change. So only F equals to ma. So acceleration will only change. Only there will be a constant acceleration. Only velocity will be changing. Okay, so force is fixed, and why it is named as FSW, because the force is acting on S, and it is coming from body W. The worker's body is W. Okay, the value is given. So we if the sled starts from the rest, so initial velocity is 0, then we need to find out the final velocity. Okay, this problem. How to solve this problem? Now we need to first find out the free body diagram. This is the body. So let us, though this is an extended object, but we can consider it to be a particle. Hope you remember in first day's discussion we had said that we sometimes we consider extended bodies as a particle for the sake of simplicity. So we are considering this to be a particle, and we are seeing the force. The force is applied to this direction, which is FSW, a vector, and also a reaction force will be acting, which is coming from the W to the coming from S to the W. So FWS, or we have written it here F dot SW. Okay, in the opposite direction. Now from this free body diagram, it will be your homework along with some other problems. In this week, you need to solve this problem and also some more problems like this. Okay, a quiz will be given to you. In that there will be some problem. So till this, if you have any doubt, you can ask me. Okay, if you don't have any doubt, so you can say that our lesson is completed for today. I will be sending you a quiz shortly. Okay, I have uh, collected your attendance from this Google Meet, and also I will collect attendance from the quiz. You please attend that quiz very positively within 4 p.m. today. And also I'll be sending you the assignment for this week. You will be given 2 or 3 days. Please solve that assignment and ask your friends to be attentive because the attendance is not satisfactory today. Okay, so thank you all. I'm ending the meeting.